So our next speaker is Yutzi Qing from Tsinghua University, China. He'll be presenting low-quality training data only, a robust framework for detecting encrypted malicious network traffic.
Hello everyone, and welcome to my presentation. Our work is about a robust framework for detecting encrypted malicious network traffic against low-quality training data. I'm Qing Yuqi from Tsinghua University, and this work is collaborated by Tsinghua University and George Mason University. As we all know, machine learning and deep learning is effective in detecting encrypted malicious traffic when compared to traditional payload-based detection method. However, most machine learning and deep learning methods rely on high-quality training data, which is time-consuming and hard to collect. So what if we only have low-quality training data? First, what's the low-quality training data? We claim that it has two main characteristics or problems. The first one is non-negligible label noises. Since public service like VirusTotal, their labels of website or traffic are different from year to year. The second, manually labeling is of large overheads, especially when facing the encrypted traffic. The second problem is insufficient malicious training samples. This is mainly because our typical approach of collecting malicious traffic, we always use some malware we captured in the real world and then execute them in the sandboxes. However, malwares in the real world keeps evolving, which makes the malware we captured is outdated. So collecting time-sensitive malware data is difficult. Due to these two main problems, low-quality training data can lead to poor performance of machine learning and deep learning methods for detecting malicious traffic. There are some potential solutions. First, we can use some robust machine learning methods against the label noises. However, they rely on strong assumptions or expert knowledge. We can use data augmentation method, but label noises will badly affect the performance of data augmentation models, which can result in more label noises. At third, we can use some pre-training model with a large-scale unlabeled data sets. However, this is time-consuming, and it may also increase the risk of privacy leakage. So our goal in this paper is detecting encrypted malicious traffic accurately using only a low-quality training data set. Unfortunately, we got a key observation about the data distribution of network traffic. It can be described as the distribution of benign data is denser, while the distribution of malicious data is sparser. Here on the left is a figure about our key observation, and on the right is our empirical study about data distribution on 3 public data sets, which results support our key observation. So if we can, like the figure on the left, we can draw a function figure about the sample density or other distribution metrics function in the feature space. We can simply draw a vertical line to split all samples into low-density samples and high-density sample, and we can relabel the high-density sample as normal and relabel other sample as malicious. Still, there are some samples that may lie around the line that is hard to identify. This is a challenge we'll talk about later in the label correction module. So our core idea to address the low-quality training data problem is leveraging the difference in distribution between benign and malicious samples to infer the true label of training samples and then generate new malicious training samples that can represent new type of malicious traffic. So according to our core idea, here's our framework. It contains 3 modules. The first module is the feature extraction module. It can convert the raw encrypted traffic into feature vectors. And then is the label correction module. It can estimate training data's distributions and then detecting and correct the label noises. The third module is the data augmentation module, which can generate new training data that can represent new type of malicious data. So here is our first module, the feature extraction module. It faces two challenges. The first one is the traffic is always encrypted by various type and versions of encryption protocols. The second challenge is the non-negligible label noises will result in inaccurate feature selection or feature extractors performance. So our solution to this is we use a sequential autoencoder model in an unsupervised manner, which can first learn the most representative features and as well as minimize the effects of label noises. Our design is we first using packet length sequence, and then we use GRU as the unit of autoencoder framework to extract the feature vectors. So we got feature vectors of all training sample and as well as the testing samples, so we can do our label correction. It also faces two challenges. The first one is high dimensional feature vectors distribution is hard to accurately estimate. And the second challenge is the difference between normal and malicious data. A part of normal and malicious data distribution may be not so significant to identify. That is the challenge I mentioned before in the samples around the vertical line. So our design is first we use MADE. It's a deep generative model which can output the probability density function in the feature space to estimate traffic data's distribution. And our solution, the second step is we first relabel part of training samples that have the most significant distributions, and then we utilizing these samples to infer other samples labels with example learning of machine learning method. So our design to this is first we're using probability density output by MADE to identify the training samples that have the most significant distributions, and then we build an example of 7 classical machine learning classifiers to relabel other samples. So we got denoised training data sets. So here is our data augmentation module. It also faces two challenges. The first one is the generated data should be diverse, otherwise it may limit the model's generalizability. The second challenge is new malicious samples distribution may not be same as the existing training data. So we should use some specific model to generate new data. Our solution is that we first predict the potential regions of new malicious samples, and then we sample from this target region with some proposed model. Our prediction about the potential regions is under 2 conditions. The first condition is the picture on the left. The condition 1 is that attackers may mimic normal behaviors to evade detection, which can be described in the feature space as these are the malicious samples that are similar to normal samples. The second condition is that new attack methods are emerging unpredictably, such as zero-day attack, so which can be described in the feature space as these are the malicious samples that are unique from all the normal and malicious samples. At last, to avoid the data imbalance problem, normal samples should also be generated around the normal samples area. So these are the 3 potential regions of the samples that should be generated. And how can we generate samples from these specific regions, since existing augmentation method can only generate samples similar to existing samples? We propose an improved GAN to address this problem. This GAN can fit 3 specific regions distribution to generate samples. Our design is first we formulate 3 specific regions with MADE's probability density function, and then we design 3 generators for 3 regions respectively in 1 GAN. You can see the figure on the right. It has 3 generators and only 1 discriminator. And at last, we calculate new loss functions for each generator, and then train the GAN and the GAN can generate the samples fit the 3 specific regions we mentioned above. That is all about our framework, and here is the evaluation part. First is our setup. It contains datasets, baselines, metrics, and the label noise ratio and training size settings. Our first part of evaluation is the overall performance. When the original label noise ratio is up to 45%, our system get a best F1 score and showing an average improvements over 200% and can up to 350% over all the baselines. And second, we also do some experiments on real-world label noises. We imitate the real-world label noise by mislabel benign data with unseen or uncommon domain name and mislabel malicious data with a specific attack type as if their threat intelligence is absent. So the result shows our system can also achieve improvements of over 150% over all the baselines. We also do some module tests to evaluate our label correction and data augmentation method, and it shows that 2 models are both more effective than baselines. And we also do some parameter-sensitive analysis. It shows our framework is insensitive to all hyperparameters. At last, we perform a real-world experiment. In total, we obtain over 2,900,000 benign samples and 790,000 malicious samples ranging from November 2017 to February 2021, which are collected by a network security enterprise. We use the traffic data in 2017 for training and the rest of the data as for testing. The result shows that our system improved baseline from around 90% up to 445% at an average of 272.5%. So here is our discussion about our work. First, when our system faces the extreme label noise, our system still get a not so bad F1 score. And we also have some procedures to reduce the extreme label noises less than the 50%. And the second, our system can be trained fast with small overhead. And the third part is the long-term deployment. Since our model has small overhead, our model can be efficiently retrained to adapt a new normal traffic in long-term deployment. Even if the collected normal samples are diverse, we can also cluster them to reduce such diversity and then process each cluster individually. And last, we talk about evading detection. Since our system has built-in design of adversarial learning, such as we generate samples that imitate the evasion samples, our system can, to some extent, handle the evading malicious traffic. So that's all about our work, and thanks for listening. Any question is welcome.
Hey, hi, thank you for the presentation. Going to the IDS dataset, it has a disproportionate amount of DDoS traffic, and the dataset has standard deviation, mean, whatever. So did you just get the F1 scores for each of those labels due to the multi-label classification, or how are you calculating the F1 score on that dataset?
If you ask, do you ask how can we identify the dataset I used in the paper is all without label noises?
No, the thing is, that dataset particularly has a lot of DDoS traffic and not DDoS traffic, distributed denial of service traffic, which is in the millions or whatever, and the other traffic, the web attacks, the intrusion attacks, isn't as much. So the F1 scores might be a bit skewed by it.
Oh, you mean the malicious sample is not as much as the normal samples?
No, the malicious are there, but the labels, the DDoS traffic
class
DDoS?
has more samples than the other classes?
Oh, where's my slide? The data sets we use, we just use the malware data sets and data sets when, sorry, you mean this page? We didn't use the traffic with DDoS since our we detection the traffic as is in flow level. So DDoS is actually is truly a difficult thing to deal with when we process the traffic in flow level because it contains many flows in one attack. So this is a good question, and we will deal with all type of attacks and in our feature work, including the DDoS and other intrusion of network that shows the strong severe problem. Thank you.
Any other questions? So yeah, I had a question. So you mentioned how your system is somewhat robust to adversarial attacks because of the way the model's generating augmented samples. And I was wondering, did you do any tests to see how an adaptive adversary performs against your system, whether the added samples around the normal distributions of benign traffic actually helps against defending against the adversary or not?
You mean how effective is our data augmentation module?
Yeah, against adversarial machine learning and adaptive adversaries.
The performance of the detection is that we use one type or several type, not all the type of attack in the data sets for the training, and the other training we will see them as the evading or some absent intelligence or unseen, unknown attacks. So the performance is to some extent shows our ability to against the evading attack, the evading malicious traffic. Thank you for the question. Thank you.
Okay, let's thank our speaker one last time.